We will begin this unit on atoms, molecules, and ions by reviewing the early history of chemistry and certain fundamental chemical laws. As was previously reviewed, measurement is an essential operation in chemistry. Antoine Lavoisier conducted several experiments in which he carefully measured the weight of the reactants and products of various reactions. His work led to the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. Following Lavoisier, Joseph Proust performed several careful weighing experiments to study the course of chemical reactions and determine the composition of various chemical compounds. He developed the law of definite proportions, which states a given compound always has exactly the same proportion of elements by mass. For example, he analyzed the substance copper carbonate, which is always 5.3 parts copper to 4 parts oxygen to 1 part carbon by mass. After Proust, John Dalton began to think about atoms as the particles that might compose elements. He reasoned that if elements were composed of tiny individual particles, a given compound should always contain the same combination of these atoms. He was able to explain why the same relative masses of elements were always found in a given compound. He continued his work by analyzing compounds of carbon and oxygen, and he found that they form two different compounds that contain different relative amounts of the elements, and the results of his work are shown in the table below. You can see that compound 2 contains twice as much oxygen per gram of carbon as compound 1. Dalton was able to easily explain this by the number of atoms. Compound 1 could be CO, or 1 carbon and 1 oxygen, and compound 2 could be CO2, or 1 carbon to 2 oxygens. He used his results to develop the law of multiple proportions that said when we analyze compounds with a series that are in a series, the ratio of the masses can always be reduced to small whole numbers. This principle was found to be able to be applied to compounds of other elements as well. Dalton is most known for his atomic theory, which has a couple general principles. He said each element is made up of tiny particles called atoms, that atoms of any element are identical, that compounds are formed when atoms of elements combine with one another, and chemical reactions are a result of the reorganization of atoms. Now let's review the structure of an atom. As we will learn later, the chemistry of an atom mainly results from its electrons. For this reason, chemists are satisfied with a pretty crude nuclear model of the atom. As you may recall, electrons have a negative charge and they are found in the area outside of the nucleus. The nucleus, or the center of the atom, contains positively charged protons and neutral neutrons. So if we look at the table below, we can see the relative charges of each of these subatomic particles as well as their masses. Note the proton and neutron have the same mass, and an electron is quite a bit smaller than the other two particles. Atoms of different elements show different chemical behavior because of differences in these subatomic particles. If we look a little bit more closely at the nucleus, it's very small compared to the overall size of the atom, and it's very dense, containing all those protons and neutrons, and accounts for almost all of the atom's mass. Let's look at a familiar element, sodium. A sodium atom has 11 protons in its nucleus. Since atoms are neutral, the number of electrons must equal the number of protons. So sodium also has 11 electrons moving around its nucleus. Even though a sodium atom always has 11 protons and 11 electrons, sodium atoms can have a different number of neutrons in the nucleus. These are called isotopes. These isotopes have almost identical chemical properties. The only difference is the number of neutrons. In nature, most elements do exist as a mixture of isotopes. We have several different ways of representing elements in chemistry. This is one format where we have the chemical symbol and then two numbers written to the left of the symbol. The first number is the atomic number and is designated Z, and it tells you the number of protons, and it's going to be written in the lower corner of the element symbol. The other number is the mass number, which is sometimes abbreviated A, and that tells us the number of protons and neutrons, and that's in the upper left-hand corner. So how do we determine the number of neutrons then? We must subtract the mass number and atomic number to give us the number of neutrons. Let's look at an example. We're asked to write the symbol for an atom that has an atomic number of 9 and a mass number of 19. Then we must figure out how many electrons and neutrons the atom has. Well, since the atomic number is 9, that means that it contains 9 protons, and if you look at your periodic table, fluorine is the element with the atomic number of 9. So we can represent fluorine in that same format with the mass number of 19 in the upper left and the atomic number in the lower left-hand corner. Since the atom has 9 protons, it must also have 9 electrons in order to be neutral. And again, since the mass number gives the total number of protons and neutrons, if we subtract these two, we are able to determine that it contains 10 neutrons. It was John Dalton who first recognized that compounds are a collection of atoms, but he couldn't figure out why the atoms were bound together. During the 20th century, we learned that an atom's electrons participate in bonding. We're going to discuss bonding more thoroughly later, but right now let's review the basics. Chemical bonds are a force of attraction that are going to hold atoms together in a compound. They can be formed in 2 different ways. First, by sharing electrons, which is going to lead to a covalent bond, and a covalently bonded compound is called a molecule. There are a couple different ways that we can represent molecules or covalent compounds. The simplest method is the chemical formula, where the symbols of the elements are used to tell us the atoms present, and then a subscript tells us how many of each type of atom. So for example, a very familiar compound, carbon dioxide, is CO2. This tells us that each molecule contains 1 carbon atom and 2 oxygen atoms. There are a couple other ways of representing molecules. We can use the structural formula, which shows us how the atoms are bonded together, but it might not tell us the actual shape. The space-filling model will show us the size of the different atoms and how they're oriented in space. And then the ball and stick model. Here are some diagrams of each type. Again, the structural formula just shows us how everything is bonded together, but not the shape. The space-filling model, which again shows us some information about size. We can see that the carbon atom in the center is quite a bit larger than the 4 hydrogen atoms. And then finally the ball and stick model, which gives us some information about the 3-dimensional shape of the molecule. Now, if compounds are not covalently bonded, they may involve ions. An ion, as you may remember, is a group of atom or atoms with a net positive or negative charge. The most familiar ionic compound is sodium chloride or table salt, which is formed when chlorine and sodium react. When sodium loses or has 1 electron removed, it now has a net charge of positive 1 and has become a positive ion, which is called a cation. When this electron is transferred to chlorine, it produces a negative 1 charge and becomes a negative ion, which is called an anion. Because these ions have opposite charges, they attract to each other and form an ionic bond. Now let's take a look at the periodic table and review some general principles. Again, each element is represented by a tile on the periodic table. The symbol is in the center. The number at the top is our atomic number or number of protons. And then the number down below is the relative atomic mass, which we'll talk about more closely a little bit later. The periodic table is organized in a couple of different ways. The vertical columns are called groups or families, and the elements in those columns tend to have similar chemical properties. The horizontal rows of elements are called periods and have similar electron structure. If we look at the periodic table, there are some trends that we can deduce. The alkali metals, or the group 1 elements, typically form a +1 charge when they become an ion. The alkaline earth metals have a +2 charge. Halogens are -1, and then noble gases don't tend to form an ion. A little bit more about the periodic table. There are 3 main groups. Most of the elements are categorized as metals, and they have certain characteristic properties, such as being good conductors of heat and electricity. They can be pounded into sheets or drawn into wires. They tend to be shiny, and they lose electrons to form positive ions. So all of the blue elements in this periodic table are classified as metals. The brown or tan elements are nonmetals. They tend to gain electrons to form negative ions, or if they bond with each other, they form covalent bonds. The last category in the green tiles in the center are metalloids, and they tend to possess properties of both metals and nonmetals.